Hello everyone. This lecture is specially recorded for first year BSc student of BK Birla College, Kalyan. This is Calculus Paper 1. In last lecture, we have defined supremum and infimum of a set. We have also seen the supremum and infimum of a set. In this lecture, we will show that whenever supremum and infimum of a set exist, then it is unique. So let's write down the result. If S is non-empty set, S subset of R, so let M belongs to R such that M is equal to supremum of S, then M is unique. Proof of this. So proof of uniqueness is always proved by method of contradiction. So we will assume that suppose the supremum of S, that is M, is not unique. So we will assume there are two real numbers which are supremum of S. So let it possible supremum of S is not unique. This would imply there exist two real number, say M1 and M2, belongs to R such that M1 is not equal to M2 and M1 comma M2 are supremum of S. When I say M1 and M2 are supremum of S, this would imply M1 and M2 are upper bound of S. So if M1 is equal to supremum of S, that means M1 is least upper bound, of S. It means that if you take any upper bound of S, then M1 is going to be the smallest upper bound of S. Also, we know that M2 is upper bound of S. So this would imply there will be a relation between M1 and M2. Since M1 is a supremum of S and M2 is a upper bound of S, that would imply M1 must be less than equal to M2. The reason is M1 is supremum of S, means it is the least upper bound among all the upper bounds. So let me call this as star. Similarly, M2 is equal to supremum of S. Also, we know that M1 is upper bound of S. So M2 is least upper bound and M1 is upper bound. So this would imply M2 must be smaller than M1. This I will number as double star. So you could see that in a star M1 is less than equal to M2 and in double star M2 is less than equal to M1. So from star and double star, star and double star, we will get M1 is equal to M2, which is a contradiction because we have assumed that M1 is not equal to M2. So why we got a contradiction? We got a contradiction because we assume that the supremum of a set is not unique. Hence, our assumption is wrong. That is, supremum of S. So instead of that is, I say that would imply supremum of S whenever exists. It is unique. So uniqueness of a supremum we have proved. On the same line, one can prove that infimum of a set whenever exists, it is unique. So let me write down that result. So result, if S is non-empty, S subset of R, a real number small m is equal to a real number small m is equal to infimum of S, then m is unique. So on the same line, you can again prove, you can say small m1 and small m2 are infimum of S and which are distinct, and you will have two inequality, m1 less than equal to m2 and uh, m1 greater than equal to m2. This two inequality will imply small m1 and small m2 are same, and this would imply that whenever infimum exists, then it is unique. So this property we can prove very easily. That's not difficult. In fact, it goes on a similar line. So the proof I am not doing, this proof is an homework. There is a nice property called as a continuum property. So let me write down this. So in the continuum property, there is a result called as a order completeness of R. So the LUB axiom or some people call it as order completeness of R. So what it says every non-empty subset of R every non-empty subset of R that is bounded above has supremum in R. So if you take any non-empty subset of R, and if the set is bounded above, then it is going to has supremum. This order completeness property is very important. We will not prove this, but this property will plays a very important role. So there is one result. This result says that second property, every non-empty set S of real number that is bounded below has an infimum in R. So this theorem can be proved with the help of, we will prove this with the help of, so proof is with the help of order completeness property of R. So OCP means order completeness property of R. What is order completeness property of R? Order completeness property of R is every non-empty subset of R that is bounded above has supremum in R. So if we know this order completeness property, then only we will prove this result. So maybe I'm not doing timing this result because my target for this lecture is to prove the characterization property of supremum and the characterization property of infimum. So timing, we'll keep this proof on a hold. So we'll revisit, not in this lecture, maybe in upcoming lectures, we will revisit this theorem definitely, or I will give you the outline of the proof that can be proved with the help of order completeness property. So let me go to the characterization property, which is my target for the today's lecture. So let us write down characterization properties of supremum. Characterization of supremum. The characterization of supremum which I am giving is basically an equivalent definition, or it gives an equivalence of a supremum. So the supremum definition of supremum can be replaced with this characterization property. So what it says, so the result is as follows. Let S is non-empty, S subset of R, let capital M belongs to R, then M is equal to supremum of S if and only if first M is an upper bound of S, and second property, for every epsilon greater than 0 there exists an element A belongs to S such that M minus epsilon less than A less than equal to M. So M is supremum of S if and only if it should satisfy these two conditions. So when I say if and only if, that means it's a converse part also I need to prove. So many a times people, instead of using M as a supremum, that definition, instead of writing definition, people write these two parts. So even you could realize that this second statement, so because a supremum of S definition is nothing but, when we say M is a supremum of S, as per the definition, it says that M should be upper bound of S, which is same as the first property. And the second part in a supremum definition is, if capital K is any upper bound of S, then M is less than equal to K. That is what in a plain language, English language. But in a mathematical, that writing that is equivalent to saying that if you take any epsilon positive number, then you can always find a real number S belongs to S, such that the A lies between M minus epsilon to M. So existence of this A is very important, which is same as for any upper bound K uh, of S, M is always less than equal to K. That second part in a definition of supremum is replaced by this mathematical expression. So maybe you may feel that you may not find the time being it is difficult to imagine this all. Maybe as those who could able to imagine, then well and good. If those who not, then still in a theorem proof of the theorem, I hope that the many things will be more clear. So let's prove this. So since it is a converse part is also true, so let's do the first part. So what is given? It is given that M is equal to supremum of S. So if M is a supremum of S, it is also given that S is non-empty set. S is a subset of R. And in a second part, it is given that M is a supremum of S. So by definition of supremum, it says that M is upper bound of S. So I have to prove this two. If M is a supremum of S, then I should prove this two statements. So first statement says that M is an upper bound of S, and second, for every epsilon greater than 0, there exists an A belongs to S such that M minus epsilon less than A less than equal to M. So you could see that the first statement has been proved very easily. That's a trivial. This does not need much information. So only definition part is enough. So this would imply first statement proved. Now I have to prove the second statement. Second statement means for every epsilon greater than 0, there exists an element A belongs to S such that M minus epsilon less than A less than equal to M. That is what I need to prove. So let epsilon be any positive real number. Suppose assume that epsilon is a greater than 0. Then suppose if M minus epsilon is upper bound of S. So let me assume that M minus epsilon as a one of the upper bound of S. But I know that it is given that M is a supremum of S. So M minus epsilon is a upper bound and M is a supremum. So when I say M is a supremum, so M is a least upper bound. But capital M is least upper bound of S. So I got two upper bound. One is M minus epsilon and the second one is M. But M is a least upper bound. So this would imply M must be less than equal to M minus epsilon. So M is less than equal to M minus epsilon. That means this epsilon must be negative. Then only this inequality holds. So this would imply epsilon must be less than equal to 0. But it is a contradiction because epsilon cannot be less than equal to 0 because at a starting only we assume that epsilon greater than 0. So that's an assumption. So why we got a contradiction? Because epsilon is greater than 0. So why we got this contradiction? Because we assume that m minus epsilon is the upper bound of S. So that would imply m minus epsilon is not an upper bound of S. So if m minus epsilon is not an upper bound of S, that means you can always find an element from the S such that m minus epsilon is strictly less than that element. So that would imply there exists an element A belongs to S such that my m minus epsilon is definitely less than that element. Let me call it as not 1, I will say star. Right. So also if A belongs to S, that would imply A is less than equal to M. Why so? Because since M is supremum. So when I say M is a supremum of S, then M is the upper bound of S. So definitely A will be smaller than M. So let me call this as double star. So if I club star and double star, then I will get from star and double star M minus epsilon is strictly less than A is strictly less than equal to M for any epsilon greater than 0. So this completes the statement number 2 which I wanted to prove. So this would imply statement number 2 proved. So I have proved statement number 1 and statement number 2. Now let's go converse part. So conversely, it is given that number 1 M is upper bound of S. Second part, if for any epsilon greater than 0, there exists A belongs to S such that M minus epsilon less than A less than equal to M. What I have to prove? To prove that M is equal to supremum of S. So when M is going to be supremum, provided M should satisfy two conditions. Condition number 1, M should be upper bound of S. And condition number 2, if K is any upper bound of S, then M should be less than equal to K. You could see that the condition number 1 is easily getting satisfied. So from given one, so I did not have to worry about the condition number 1 because given one basically gives me, you can write down, let's write down from given 1, M is upper bound of S. So let me call this as a statement A. Now I need to have a statement B. The statement B which I interested to prove is as follows, that if K is any upper bound of S, then I should prove that M is less than equal to K. So now to prove that, if K is any upper bound of S, then k must be larger than my m. This is what I wanted to prove. So how will I prove? To prove this, again, we have to use the by method of contradiction. Suppose this statement is not true. We assume that suppose k is an upper bound, but m is not less than equal to k. M is strictly greater than k. So suppose k is any upper bound such that m is greater than k, right? Because if it is not true means k is any upper bound of s, then m less than equal to k. So for negation of this, if k is any upper bound of s, implies m is strictly greater than k. So that is what negation, because if you imply in a implication, true false is only false. So this is true. This I supposed to make it false so that the resultant answer is false. If you know in a logical table TF, and if you take only implies, then TF only is false. Rest everything is false. Rest everything is true. So this is logical table that you should know this. I'm sure that you will able to recall that. So I have assumed that if k is any upper bound of s, then m is strictly greater than k. So uh, if I assume that this, then I should get a contradiction. So since m greater than k, this would imply m minus k is greater than 0, right? And if you remembered in a given, the second part says that it is given that for any epsilon greater than 0, there exists a belongs to s such that m minus epsilon less than a less than equal to m. So it says that for any epsilon greater than 0, so you take any positive real number. So what I will do, take epsilon is equal to m minus k, because it's a greater than 0. Then from given 1, if I go to given 1, I should say given 2, what I will get, given 2 says that m minus epsilon less than a less than equal to m. So given say 2 says that m minus epsilon, I will replace it by m minus k strictly less than a less than equal to m. So this will get cancelled and I will have minus minus becomes k. So k less than a less than equal to m. So from given to, I should say that there exists a belongs to s such that m minus epsilon. So m minus, instead of epsilon I have written m minus k less than a less than. So what I got is as follows: k is less than equal to k is less than a less than equal to m. This would imply k less than a less than equal to m. Right, but it is a contradiction. Because why it is contradiction? Because I have said that k is, because since k is upper bound of s and a belongs to s, this would imply a must be less than equal to k, and whereas here I got a less than equal to k, a strictly less than k, k strictly less than a, which is a contradiction. Because if k is upper bound of s and a belongs to s, then definitely a should be smaller than that upper bound, which is a contradiction. Why we got a contradiction? Because we assume that k is any upper bound such that the of s such that m less than greater than k. That's a wrong statement. Hence our assumption is wrong. Hence our assumption is wrong. Hence our assumption is wrong. This would imply for every epsilon, for any k, for so this would imply if k is any upper bound of S, then M must be less than equal to K. So let me call this as capital B. Somewhere I have stated capital A also. Let me see where I have stated capital A. Yeah, this is A. M is upper bound of S, and I have stated now capital B also. So from A and B, we can say that M is equal to supremum of S. So this completes the theorem. Of course, when I have proved the characterization of supremum, on the same line we have characterization of infimum. I will not prove that theorem now, but I can state that. So characterization of infimum. It says that if S is non-empty, S subset of R, then small m is equal to infimum of S if and only if number one, M is lower bound of S, and second, for any epsilon greater than 0, there exists A belongs to S such that small m less than equal to A strictly less than m plus epsilon. So proof of this is not difficult. One can follow the same steps which I have applied for the characterization of supremum. Those who have understood characterization of supremum, they can easily prove the characterization of infimum. So this proof could be a homework. So maybe in class or in lecture, we will discuss the proof of this theorem. So thank you. Thanks a lot.